Welcome back to an introduction to the Discrete Fourier Transform. In this lecture 2, we'll talk about digital audio basics. In the first lecture, we discussed how Discrete Fourier Transform works and how Python can be used to manipulate and analyze audio files. In this lecture, we'll talk about basics of audio signals. What is sound? Sound is simply some kind of an object vibrating. So, for example, a tuning fork, vocal cords, or a string. And this causes local regions of the air to have compression regions and rarefaction regions. So compression regions are where the air, the pressure is higher than the ambient or the background pressure, and then the rarefaction regions are where the pressure is lower than the background air pressure. So this is all relative. This waveform of air pressure is relative to the background air pressure, and so a microphone that picks up the signal, if I plug that into an oscilloscope, then you get this kind of a signal, a continuous signal. So that signal is picked up by the microphone. Again, here's an oscilloscope representation of that continuous signal. And because computers can't store all this information, the continuous information, what it does is that this signal is fed into an ADC, which is an analog to digital converter, and that simply take that continuous signal and samples it and then convert it into a stream of numbers. So here's the continuous signal. Sampling it means pick out certain values at equal intervals from that signal. And so really digital audio is simply this array of numbers. So the standard rate for CD quality is 44,100 samples per second. And so here's the analog signal, the continuous function. We sample it, we get an array of numbers, and so these numbers could be could have different memory allocation for it. So for example, I can choose to represent each of these sample with a 16-bit value. And so that's called the bit depth of the sample. One of the bits is for sign, plus or minus. The other 15 bits is for the value of the signal. And so this process can be reversed. If I have an array of numbers, I can send it to a digital to analog converter and convert that into a voltage or a current that is continuous, and then that current power the speakers. And it turns out that actually the sample that we have, because we sample at 44,100 times a second, the speakers have to vibrate or move 44,100 times a second to reproduce that exact signal. So it's kind of amazing that a sound file is just simply an array of numbers. And in fact, we saw this in the last video. So again, this is the Jupyter notebook. I want to import all these files just like last time. And then last time we saw that we can import a piano text file, which is an array of numbers, into a Python variable called ys using the np.loadText function, and then I can create an audio object with those array of values, and then we specify the rate, which is the standard rate. So if I run this, then I have an audio object. I can play it. So that's the piano sound of a note. And in the last video, we actually talked about how to use Discrete Fourier Transform to kind of analyze that signal. And so I want to talk about some basic signal processing. So we have a function which is periodic. So that means that it repeats over and over again. So the time that it takes for it to repeat is the period, and the amplitude is the height from the equilibrium to the highest point, and then the period is 1 over the frequency. So let's do an example of this. So here's the function. Notice that if I look at one cycle, it takes about 1/3 of a second. So the period is 1/3 a second per cycle, and then the frequency would be the reciprocal of that. And notice that the frequency is basically measure how many cycles it takes for this function to go in 1 second. And so in this case, in 1 second, it actually completes 3 cycles. So that's the frequency of this signal. It's the number of times that it can finish a cycle, the number of cycles that it completes in 1 second. Here's a sine function that you might remember from pre-calculus or algebra 2. This function has an amplitude of 1 and then has a period of 2 pi. Here's a cosine function. It's the same thing as the sine, except that you shift over by pi over 2. And so these are basic sine cosine functions. They complete 1 cycle in 2 pi seconds. And so it's actually easier to kind of factor out that this 2 pi. So if I were to, so again, this is the sine function, for example. In this interval, it completes 1 cycle in 2 pi seconds. But if I take out the 2 pi and I put it here, then this function actually completes 1 cycle in 1 second. So in the interval 0 and 1, it will actually go through 0 to 2 pi. So therefore, this is 1 cycle per second. So this is a 1 hertz sine wave. Then if I add into that a number f, then this function in 1 second will complete f cycles. And so so this is a function that completes f cycle in 1 second, so therefore it has a frequency of f hertz. So this is kind of a nice form to represent function that depends on the frequency. So it's so we're going to use this form throughout the rest of this lecture. In general, we usually write these sinusoids in this form. So A is the amplitude, again F is the frequency, and then this phi right here is the phase of the sinusoid, and the same thing for cosine. So again, A is amplitude, F is frequency in hertz, then the period is 1 over F. These are reciprocal, and then phi is the phase measured in radians. So the phase is simply, if I plug in t for 0, the phase is basically the angle that the function starts. And then there's also this idea of an angular frequency. So this f is regular frequency. It measures the number of times that the number of cycles per second. Angular frequency measures the number of radians per second. So you simply take the number of cycles per second, you multiply that by 2 pi, and you get the number of angles per second. So for example, here's a function. The amplitude is 3, the frequency is 4, so this function completes 4 cycles in 1 second, and then the phase is pi over 2, and then if you want to compute the angular frequency, then that is going to be 8 pi radians, because every cycle is 2 pi, we're completing 4 cycles, so that's 8 pi per yeah, it actually should be 8 pi radians per second. So that's a typo there. So middle C has frequency of about 262 hertz, and so I can represent that with this sinusoid, sine of 2 pi, and this is f times t, and so so this means that this is a middle C signal, and it's a 2 seconds signal. So notice this is a nice way to represent that. You plug in the frequency right here, and then that represents that frequency. The C major chord has 3 different notes, C, E, G, and those has these frequencies. So I can represent it using this function. You just basically add up the three functions together, and then you get that that major chord. So again, here's the 3 frequencies of C, E, and G. So let's try to do this in Python and see what these sounds like. Okay, so we want to sample the function that has this frequency, which is middle C, for 2 seconds. And so first the sampling rate is going to be 44,100 times. And so from that we can figure out how many samples this will take. So if this is the number of samples in 1 second, then I want to multiply that by 2 to get the number of samples in 2 seconds. And then now I want to create the time that I sample, or the time that I sample. So I'm going to do np.linspace. This is for the function that we talked about in the last lecture. And I want to go from 0 to 2 seconds. And I want a total of n samples. So this is an array of n numbers from 0 to 2, equally spaced. And then finally I get the y values by applying the sine function. So it's 2 times np dot pi times the frequency is 261.6, and then the time is ts. So it takes all these numbers in this array and then I apply it to this function. So if I do that, I can now create the audio object with those y value and at the rate of fs. So if I do that, I've created a sound here. So here it is. So this is the sound like a tuning fork vibrating at this middle C frequency. So here it is again. Let's try to do this chord also. So I think this is yeah, so this is exactly the same thing. So I'm going to just copy this code here, and then I'm going to paste it here. And so except the only difference here is that I want a different function. So this is the middle C. I also want to get the other two notes. So 261.6, and then I also want, oh actually I actually want this to be the F major chord, and so in that case I want 174.6, then I want 220. 220 is the A note, and then I also want 261, which is the C note. So this is the F major chord, F, A, and C. And so if I do that, I can now play this. So there's the F major chord. But if you notice that doesn't sound too nice, and so I'm gonna use the the wave file from last time. I'm gonna read in this wave file, F major dot wave. Then I'm gonna play this one and see the difference. This is F major. Notice this is a big difference. The reason is because this is, of course, played on the piano, and it has all the harmonics, give it that richness of that chord. Okay, so let's talk more about that. So loudness is our brain's perception of amplitude. So we saw in the function the amplitude, the bigger that is, then the louder the sound. But pitch is our brain's perception of frequency. And so we saw the different frequency there and how our brain interprets them differently. And in fact, it turns out that this perception is actually based on the logarithm scale. And so the interval is between two notes is the perceived difference between the two pitches. And so what that means is that because this is a logarithm scale, the interval that we hear between two notes actually depends on the ratio of their frequencies and not the difference of the frequencies. So let's talk more about this. So for example, A3 has this frequency, A4 is 440, and the difference here is 220. From A4 to A5, this difference is, notice these are doubling of frequency. So an octave is when you double the frequency. So A3 is 220, A4 is 440, and A5 is 880. So the difference here is a difference of an octave. But on a frequency scale, this is actually doubling each frequency. So notice the difference here is much bigger than the difference here, but that doesn't matter because our perceived difference is based on the ratio, not the actual difference. So the way we perceive this this jump from A3 to A4, so again, our perception is the log scale. So log of that frequency is how we perceive that note. Again, this is the log of 220, and our perception of the difference is you subtract those two. But if you remember from pre-calc, the log, the difference of the log is actually the log of the quotient. And so in this case, 440 divided by 220 is log 2. Now, if I look at between A4 to A5, again, same thing. The difference here gives us the difference in our perception. But again, we're dividing it by 80 divided by 440, so that's also log 2. So this says that even though this is a bigger difference than this, our perception is the same because our perception is based on the quotient or the ratio of the frequencies. not the actual difference. So another way to think about that is that on the bottom is frequency scale, and notice from here to here this is a jump, but this is a much bigger jump. But our perception, which is the log of these frequency, is this scale. This is the perception scale, and the perception scale, the difference here is the same, right? Even though this is a much bigger jump. And so that's why on the piano, for example, when we play these notes on the piano, these jumps are exponential, but we perceive them to be the same difference in sound. So on the piano, here's actually a function for the frequencies. So notice this is an exponential function, so this grows very fast. But as we go from left to right, so from the first note to the last note, so this is an 88 key piano. Even though the frequency is going up very fast, we only perceive the same difference, the same semitone difference. Notice, by the way, the first note has about 27, the frequency has 27.5 hertz. The last note is around about 4,200 hertz. Turns out that really beyond 5,000 hertz, it's hard for us to really detect the difference in different notes. So that's why realistically, if we have a piano that has more keys, it's harder for us to distinguish those keys if it goes outside of this range. So a pure tone is basically a function of one frequency. So we saw how we did that with the sine function with one frequency. But most sounds are more complicated, more complex. It has a lot more frequencies in it. So for example, if I play E4 on a piano note, it has a bunch of frequencies that it plays, and that's what it gives it that richness. And that's what it is. That's how we can distinguish between, say, an E on a piano or an E on a trumpet. Is that these frequencies will be different. And so, for example, on the E4 note, it's 330 hertz, 660. So these notice these are integer multiple of each other of the first note. So the first note is called the fundamental frequency. So that's the note of E4, and then all the other notes are multiples of it, give it that rich tone. And so those are called the other notes are called the harmonics or the overtones. And so if I were to look at the E4 on a trumpet, then maybe these might be different integer multiple. It will still have the same fundamental, but it might have different multiple of the fundamental. It might have different magnitude, might have different sizes, depends on how the instrument works. Okay, time versus frequency domains. And so we saw some of this from last video also, but in the time domain, our signal is based on voltage or current, and it's a function of time. So this is a function where the domain is time. But we talked about how we can convert that into an equivalent form, which is the frequency domain. And so that signal is represented as a function of frequencies that are present in the signal. So for example, in the last lecture, we actually did this out. We had a violin playing, and this is the time domain. This is a function of time. If we zoom in, we see this, but this domain is hard to interpret. So we take this and we convert it into the frequency domain, which is a function of frequencies. So this tells you all the frequencies that are present in the signal. And we use the discrete Fourier transform to do that. And so this is called the spectrum of the signal, all the frequencies that are present in the signal. And so we saw that from this representation, it's much easier to see the information of the signal. So for example, we saw that this is A4, about 440, and then this is the fundamental of it, so that's A5, and this is about 1320, which is actually E6, and then again this is 17, I guess it would be 1780, 1760, so this would be again a multiple of this, so this is also an A, so A4, A5, E6, and then this is A6, and then this one is actually about 2200 or so, and this is the C sharp 7. And so from this representation, we can't tell what it is, but from this representation we see that this is the A major chord, which is really amazing that we can kind of read that off from using mathematics. And so yeah, I think we actually did do this from last lecture, so please watch that if you haven't. But we had functions that actually plot the signal and then we have we wrote a function that actually give you the frequency information, and so I'll rerun this again here. But so we saw that this is the function of the violin, and then we also did the same thing for the so this is the frequency domain representation. And by the way, when you run this on Jupyter Notebook, it actually have this nice feature. Look at the bottom right here. It actually tells you excuse me, it actually tells you the coordinates. So for example, if I go here, notice on the bottom it says about 440, right? So that's how you can read off. We can, and actually in the homework you actually have to figure out these frequency exactly, but you can eyeball it, and this these numbers right here can help you approximate the information from this graph. Okay, and so the idea is that the time domain is hard to interpret, so we use the discrete Fourier transform to convert it into a frequency domain. In fact, we can actually go back, so this process is invertible. We can actually take the inverse discrete Fourier transform and take the frequency domain and go back to the time domain. So really a signal is actually determined by the frequency content of it, because this process is invertible. So here's kind of a nice GIF files that allow us to kind of see this. So this function is our signal, it's a sound signal, and it's composed of all these frequencies. So we decompose it into frequency information. And so for example, these are the lower frequency, these are the high frequency, and we compute the magnitude of those frequencies. And so this is the fundamental frequency, and these are the multiples or whatever frequency that's in the signal. So on the top is the time domain, on the bottom is the frequency domain representation. And so here it is, right? Notice also, by the way, the low frequency, this big function has a high amplitude, so it has more energy in the signal, whereas the high frequency has lower amplitude, so it has lower energy in the signal. And so when you decompose it, notice the high amplitude, low frequency signal has a higher magnitude in the spectrum or in the frequency domain, and the higher frequency on the right here has lower amplitude. So again, that's reflected by the magnitude of those components. And so time domain on the left, frequency domain on the right, and this is kind of a nice way to visualize how it works. Okay, and in fact we've seen this, you actually have seen this in real life. If you ever had a home audio system or some kind of a sound system, you might have seen this kind of a graph. And so this is actually the discrete Fourier transform. In fact, this is doing the discrete Fourier transform over small intervals. So we're doing this discrete Fourier transform conversion many times. So every time there's a picture, that's one discrete Fourier transform, and we take discrete Fourier transform for small interval over and over again, put them together, and they'll give you the spectrum of the entire song. And so if we plot this differently, sometimes they call that the spectrogram. And so the spectrogram is basically a sequence of discrete Fourier transform that allow us to kind of see the fingerprint of the song. And this is actually how that app works, the Shazam app. It takes the fingerprint of the song and then match it to a database. Okay, so here's some important takeaways from this lecture. So digital audio is simply a sampling of a continuous analog function at some rate, and you have an array of numbers that represent that audio. And then sinusoids take on this form, where A is the amplitude, F is frequency, and phi is the phase. So this is a way to write sinusoid. Makes it easy to spot the frequency information, which is what we want. And pitch is our brain perception of frequency, and we saw that was on a log scale. We saw fundamental frequency versus harmonics. And then time and frequency domains are two ways to represent the same information, but the frequency domain might be easier if we want to interpret the content of the signal. And finally, the discrete Fourier transform and the inverse discrete Fourier transform allow us to go back and forth between these two domains. Okay, so here's a list of references again. Thanks for watching.